Hello, my name is Max Keegan, and the topic that I chose for the final paper is Statcast. Statcast is a rigorous technological advancement that allows us to collect and analyze massive amounts of baseball data, and further put it to good use to draw useful conclusions. Since coming into Major League Baseball, Statcast has revolutionized the game, and will continue to do so for a long time. The subject of mathematics has applications all around the world, from the medical field to the educational field and into the world of sports. Mathematics is in abundance everywhere. As baseball fans, when we're watching the game or checking the box score, we have access to basic baseball statistics such as home runs, runs batted in, and batting average. Statcast, however, dives a little bit deeper than what the typical human eye can see. Statcast technology has been implemented all around every Major League park in Major League Baseball. All 30 teams and 30 stadiums have access to this great technology. To be more specific, the Hawkeye technology within Statcast is what is used in the stadiums. Hawkeye consists of 12 cameras and radar systems all around the ballpark. Of these 12 cameras, 5 of them are used strictly for pitching, while the other 7 are able to capture data from the hitting and fielding perspective of baseball. Within the realm of Statcast, we will focus on 3 main categories: hit effects, pitch effects, and field effects. Under hit effects, we will focus on exit velocity and launch angle. For pitch effects, we will touch on pitch velocity, pitch movement, as well as a little bit of spin rate. And for field effects, we will look at fielding efficiency, catch probability, and OAA, also known as outs above average. To begin with, we will start with hit effects. As mentioned before, we will touch on exit velocity and launch angle. Hit effects has a direct focus on batted balls and the hitting aspect of baseball, and the data we gather through hit effects is very useful when it comes to hitter analysis. First, we will begin with exit velocity, which can be defined as the velocity at which the ball comes off the bat. As exit velocity varies from plate appearance to plate appearance, it is useful to take a look at the average exit velocity of a hitter to get a feel for how hard a hitter is hitting the ball on average when he steps up to the plate. Average exit velocity, or AEV, can be defined as the sum of all the exit velocities for that hitter divided by the total batted ball events, which includes every ball that is put in play, excluding things like foul balls for obvious purposes. Take a look at the following table to see how exit velocity relates to batting average. This data is used from the 2015 Major League Baseball season. As you can see, the higher the exit velocity, or the harder the ball comes off the bat, the higher the batting average. Also, the harder you hit the ball, the more likely you are to hit a home run. As you can see, anything less than 85 miles an hour off the bat did not result in a home run for the 2015 season. So, it's safe to say that the harder you hit a ball, the more likely you are to get a hit, and the more likely you are to hit a home run. Next, let's take a look at launch angle, which is the vertical angle at which the ball leaves the bat. Using launch angle, we can categorize the type of hit. For example, anything less than 10 degrees is classified as a ground ball. Between 10 and 25 degrees is classified as a line drive. Between 25 and 50 degrees is classified as a fly ball. And anything over 50 degrees is classified as a pop-up. Similar to exit velocity, launch angle varies from plate appearance to plate appearance. So it is again useful to look at the average launch angle, or ALA, which can be defined as the sum of all the launch angles for any particular hitter, divided by, again, the total batted ball events. Average launch angle gives us a feel for the hitter and helps us define hitter tendencies, such as a ground ball hitter, fly ball hitter, etc. The graphics below exemplify the relationship between exit velocity and launch angle. On the left, with an exit velocity of 90 miles an hour and a launch angle of 35 degrees, the resulting batting average is .059 with a home run percentage of 1%, as these are all very soft fly balls. In the middle, with an exit velocity of 105 miles an hour and a launch angle of 25 degrees, we have a batting average of .958 and a home run percentage of a whopping 84%, as these are all very hard hit, line drive, borderline fly balls. On the right, we have a very hard hit ground ball with a 90 mile an hour exit velocity and a launch angle of 5 degrees. Although these don't result in any home runs, the resulting batting average is .514, which is well above average. Next, let's dive into the pitching aspect of Statcast, pitch FX. We will touch on pitch velocity, pitch movement, as well as a little bit of spin rate. For a better understanding of what's coming, take a look at the coordinate system in place. The y-axis points directly at the pitcher, while the x-axis, perpendicular to the y-axis, points directly to the right of the catcher, and the z-axis points straight up to the sky. First, we will take a look at pitch velocity, starting with initial velocity, which is the velocity of the pitch the moment it leaves the hand of the pitcher. Initial velocity, represented by v sub 0, can be defined as the square root of the sum of the squares of the initial velocities in the x, y, and z dimension, all of which are given by the pitch FX technology. In order to find final velocity, we will need an x, y, and z component of velocity, as well as the time component. We can start with the y component of the velocity, which is defined by the first equation shown here, in which the initial velocity in the y, the acceleration in the y, and the initial and final position of y are all given by Statcast technology. Once we have v sub y, we are able to solve for t, defined by the second equation shown here. Now that we have the time component, we can go ahead and find the x and z velocities. The velocity in the x direction is defined as the initial velocity in the x plus the acceleration in the x times time, and z follows the same format just in the z direction. Now with vx, vy, and vz, we can now solve for the final velocity, v sub f, which is defined as the square root of the sum of the squares of the velocities in the x, y, and z direction. Moving on to pitch movement, let's start with a little background information. Hitters typically cannot see pitch movement until the ball is about 40 feet from the plate. So, we will start by finding the time it takes for the ball to go from the hand of the pitcher to the 40-foot mark, defined as t sub 40, which is equal to the equation shown below. All of which the variables needed are provided by the pitch FX technology. As we continue, we need to find the x position and velocity as well as the z position and velocity at the 40-foot mark. Courtesy of the pitch FX technology, we have all the variables we need to solve for the four variables below: x sub 40, z sub 40, the velocity in the x at the 40-foot mark, and the velocity in the z at the 40-foot mark. As we move on, we need to solve for the time it takes for the ball to travel the final 40 feet, which is defined as t sub h equal to the total time minus t sub 40, which we just solved for. With t sub h now solved for, we can move on to find the position of the ball in the x and z directions, under the impression that the ball has no spin. This will be useful in a little bit when we come to analyze the actual movement of the pitch when the ball does have spin on it, which is the regular in Major League Baseball. Represented by x sub no spin and z sub no spin, the equations are shown below. With the no spin variables in mind, we can now assess the movement or break of the pitch in the x and z directions. Using the position of the actual pitch minus the position of the pitch if there were no spin, we can see how much break the actual ball has in both the x and z directions, which represent in and out on the plate and up and down on the plate. Branching off of pitch movement, pitchers need to put spin on the baseball in order to make it move, hence spin rate. Although there is no concrete equation for calculation, spin rate is useful when evaluating the potential a pitcher has to move his pitches. As seen in the table below, the harder a pitcher throws a ball, the less RPMs, or revolutions per minute, it will have, which makes sense as breaking balls have a lot more spin, although they come in a little bit slower. The final component we will look at is field effects, which covers all defenders on the field, but we will focus particularly on outfielders. And we will look at fielding efficiency, catch probability, and OAA, or outs above average. First, let's take a look at fielding efficiency, which can be defined as the efficiency in which a player makes a play on the ball. Fielding efficiency is defined by two factors: the straight path distance to the ball and the actual distance of the path taken to the ball. As the equation shows below, fielding efficiency equals the straight path distance over the actual path distance. For example, consider a straight path distance to the ball of 57 feet. However, the player travels a total of 70 feet to make the play. His fielding efficiency would be 57 over 70, which equals 0.814, or an efficiency of 81.4%. Another metric that Field FX provides for us is catch probability, which is the likelihood that a ball to the outfield will be caught. There are four components that make up catch probability: the distance to be covered, the flight time of the ball, the direction of travel, and the wall factor. Catch probability is assessed in bands of 5%. So for example, a catch probability of 17% and 19% will be assessed at the same difficulty. As we continue, take a look at the table below. Statcast ranks every play made between 0 and 5 stars based on the associated catch probability. For example, a catch probability between 0 and 25% results in a 5-star play if the play is made. On the other end of it, anything over 96% receives a 0-star grade, as that play should always be made. As mentioned earlier, the wall factor is assessed when looking at catch probability. This was added in 2018, and it deems plays around the wall a little bit more difficult, which results in a lower catch probability. For example, in 2017, Giancarlo Stanton traveled 96 feet back to the wall in 5.4 seconds to make the play. That year, his play received a catch probability of 55%. However, when the wall factor was added in 2018, the catch probability dropped 44% down to 11%, which makes this out to be a much more difficult play than it was. For a better understanding, take a look at the graph below, which displays catch probability on a hang time versus distance graph. Look towards the top left. The distance traveled is very low and the hang time is pretty high, which results somewhere between 80 and 90% catch probability. However, down towards the bottom right, the distance traveled increases and the hang time decreases, which makes for a much more difficult play, hence the red color, which represents anywhere between a 10 and 40% catch probability. A very useful metric when analyzing defensive talent in Major League Baseball is outs above average, or OAA. This is how many outs a given player has saved over the course of a season, and it is calculated strictly using catch probability. As you can see, OAA equals 1 minus the catch probability, or OAA can be negative, and it is simply the negative catch probability. For example, making a play on a ball with a catch probability of 35% will result in an OAA of 1 minus 0.35, which equals 0.65. However, failing to make this play results in an OAA of negative 0.35. These numbers are added up as the season goes on and results in a final OAA at the end of the season. As we conclude, we have touched on the three big components of Statcast: hit effects, pitch effects, and field effects. Statcast has already revolutionized the game of baseball, and it will continue to do so as time goes on. Right now, there is more data than ever before, and front offices and teams will continue to use this data to evaluate their players and make decisions. With an abundance of data and numerous different analytical tools, front offices can dig really deep before they make a decision on a player that they want for their roster. To me, this is only the beginning of what Statcast is able to do for the sport, and I'm looking forward to see how it grows and expands in the future.